Okay, so this tutorial is to cover the statistical tests that you can use for your internal assessment if you did a database study. So the kinds of database experiments that you might have done are something like, is there a correlation between poverty and flu incidence, or what is the correlation between cancer rates and graduation rates? So just to reiterate that the database experiments are one in which you collected information from two publicly available databases. This is not the statistical test for the hands-on experiments. For that, go over and find the one-way ANOVA tutorial. Okay, so before I get any more into this, I just want to reiterate some of the requirements for a database experiment. So if your databases do not meet this criteria, this experiment is going to get kicked back to you. So please double check that the databases that you select have exact matches in the following criteria: that your locations for each database is the same between the two. So if you have one database that has, the poverty levels by the state, then the database that you're looking at for your flu incidents also has to have those same states. You can't have one database that has, information for, say, countries and try to compare that to a database that has information on the county level. So they must match exactly. And moreover, if, like, say you're going to use poverty levels for certain cities, the locations in your poverty database have to match what you're comparing it to in the fluid incidence. Okay, so the locations have to match, and then the other thing is that your timeframes have to match. So if your database for cancer rates was collected in 2008, that means you have to go back and find a separate information source for your graduation rate also in 2008. It's not going to do you any good to compare, one thing that happened in 2020 to 2008. That's not an actual comparison. So if your databases don't fit this criteria where they match both on location and time frame, you have to go back and find another one. Do not write up your internal assessment because it's just going to get kicked back to you. Okay, and then the other thing is that you have to have at least 50 data points. Let's be real, the database experiments are far less work than the hands-on ones, so you have to find data sources that have a lot of data points for you to work with, because the bulk of your work is going to come from the analysis and evaluation sections. So find something that gives you more than 50 database points. You can't get away with just comparing 3 states or 3 cities. It has to be 50. So all of the databases that you get from, say, the World Health Organization are going to have them by country where they were easily more than 200. If you're getting anything from the CDC, it's usually based on states, so you're going to have more than 50. All right, so assuming that you clear that hurdle, there are some different options for the kinds of statistical tests you can do to determine correlation. So one of them is a regression analysis, but this is only good for fixed incremental data that you actually control. So that would be if there were an information source out there, say it was for temperature, where you had information for 1 degree, 2 degrees, 3 degrees, 4 degrees, and it's going to be testing for a linear relationship. And what it will return is an equation to describe that relationship. Another one is the Pearson's correlation, and it's suitable for quote-unquote even non-incremental data. So things like the median household level, where it's not by dollar amount going up, but it is sort of evenly distributed. And this one is again testing for a linear relationship and will return a correlation coefficient. So what I will say is that these two are somewhat limited and probably not suitable for the vast array of your projects. So the third one is the Spearmans correlation. So this is going to be suitable for non-incremental data, so things that don't go up by 1 or 10 evenly every time. And instead of limiting yourself to looking for a correlation of a linear relationship, the Spearmans correlation will tell you if there's any correlation at all. So this is overall a more powerful statistical test, and it also returns a correlation coefficient. So I'm going to recommend that you not use the regression analysis or the Pearson's correlation, that you stick with the Spearman's correlation for the reasons that I've laid out here, that you're probably not going to have incremental data, and that you want to test for any relationship, not just a linear one. That's more restricting. So let's look at this Spearman correlation experiment. So we'll go over the equation first, and then I'll show you how you do this in Google Docs. So the Spearman's correlation is called rho, and the equation that you get to calculate rho is rho is basically 1 minus 6 times the sum of something called di squared, and we'll talk more about what this is, which is the difference in rank squared, and so this will become more clear once we go into the Google Docs. And then this numerator is divided by n times n squared minus 1, where n is the number of data pairs. So remember, everyone has to have a minimum of 50, so your n is going to be at least 50 and go up to however many data pairs that you have. So the second part of calculating this is going to be calculating a t statistic, which you need rho to do, and we'll come back to that in a minute. Right now, let's just focus on how you get rho. Okay, so over on Google Docs, I have a template for you guys, and so you're going to go out and you will have collected some values, 50 different values from database 1. Maybe this is your poverty index, maybe this is your flu incidence rate, and then you will put in the next column your values for database 2. So maybe this would be, I don't know, the temperature in the area. So each one of these rows would be, say you were doing states. Well, maybe this was the poverty rate for Texas, and then immediately next to it is going to be the temperature, average temperature in, say, 2008. So you would have your two database values here side by side, and again, they're aligned by the pairs, by locations, or whatever you were trying to correlate. So to get how Spearman rank coefficient works is that what it's going to calculate is how high is a number in one column, how well does that correlate with how high a number is in this other column. And so the way that you find a rank in a data set is you say, okay, if I were to line up all the numbers in this column from highest to lowest, what place would this value be? So if I were to compare 94 to every other number in this column, what number would that be? What rank would it be? So to get that, I just push equal rank dot average, and I'm going to select this cell because that's what I want to know, like where does this number compare to this entire column. And then I can close bracket. So what this value is telling me is that if I were to line up all the numbers in this column from largest to smallest, 94 would be the second and a half, which probably means there's another 94 somewhere in there. So to copy this equation, because I don't want to write this every single time, right? I can put a $ here in between the A and the 3 and the A and the 51. And when I click and drag it, what that's going to do is compare each value in that first column. And you see it kept the A3 and A51. So for each value, it's saying this is the rank order that it would be in the numbers in this column. So now I can repeat that, and let's see if it'll let me copy paste. I doubt it, but let's see. Oh, it did. Okay, cool. So I want to do the same thing for my second database values. So all I did was copy and paste the rank average, and it's going to say, give me the rank value for each cell only in column B, which is what I wanted to do. So I should be able to drag this down, and it'll give me these values. So for the value for database 2, say again this was for Texas, this is the 24th in that rank. So if I were to line up all the values in column 2, 46 would be number 24, which is pretty different. Okay, so let's talk about this di squared. So all di squared is, and then this is from, go back. So the di squared is this part of the equation. So this is the difference in rank squared. So for this number, what you're doing is by pair location. So if I compare the rank of values in location 1 for database 1 minus the rank of the value in database 2, I take that number and I'm going to get some value. And what happens if I square that value? So what this is looking at is how close or far apart are these numbers. If they're far apart, it suggests that these numbers are not trending together. If they're close together, like this is here, so the smaller the difference between them, it suggests that they might trend together. So let's go ahead and we're going to click and drag this all the way through for each single one. And we're going to get a sum of squares because remember in our equation over here, we need the sum of squares of delta I squared, which I have here. And I know that to calculate rho, once I have this, I can pretty much fill out my equations because I have my di squared, I have my sum of squares, and I have my number of data points. So to go back over to my template here, I have my sum of squares, I have a place to input my number of pairs, which in this case is 50. And then I have a calculation for the numerator, which is 6 times the sum of squares, right? Because this is just 6 times the sum of squares. That's all that is. And then I had a calculation for the numerator, or the denominator, which is n, number of trials, times n squared minus 1. And again, n in this case is 50. So this is my numerator, this is my denominator. I just divided these two numbers by each other. And then to calculate rho is 1 minus this ratio here. And that's all this equation here. So rho is 1 minus these two numbers divided by each other. So I also have a degrees of freedom, which is going to come up here in a minute. So now I have my rho, which is 0.114. And what I can tell you is that rho values will vary between -1 to +1. And the closer a rho value is to either of these extremes suggests a stronger correlation. The closer it is to 0 means they're not having much of a correlation, which considering that these numbers, these columns were randomly generated, is probably going to be true. So my rho is equal to 0.144. So that's my rho. So I use rho to calculate this other number called a t-statistic. And so the equation for your t-statistic is rho times the square root of n, which is again your number of data pairs, minus 2, over 1 minus rho squared. So, and again, when you're writing out your analysis section, you have to put these equations in your paper. So copy these equations and make sure they're in the analysis section of your internal assessment. And then right next to it, fill it in with the actual numbers that you get right from these calculations. So to calculate your t-statistic, I just have, this is the exact same equation. So it's rho times the square root of your n minus 2, which remember n is 50, so n minus 2 is 48. But if your pairs are different, you're going to have to adjust these numbers. And so that's going to be divided by 1 minus rho squared. And so from that, I get a t-statistic of 1.01. And what I now do is I use my t-statistic and I run it through something called the t-distribution to calculate my p-value. So let's talk a minute about p-values, right, and hypothesis testing. So your question is set up as a does one factor correlate with another factor? And so what you're really doing is you're testing your hypothesis and you're trying to choose between one of two options. So the null hypothesis is that the treatment does not have any effect. There is no correlation. Your hypothesis that you set out at the start of this internal assessment is that the treatment does have some sort of correlation. That's exactly what you're testing. And the p-value that you're going to be looking for is something less than 0.05. So the p-value of 0.05 is the standard cutoff for statistical significance. And what that suggests is that if it is less than, hang on, let me fix that, p.05. So what that suggests is that there's a 95% chance that what you're seeing, the trend you're seeing, is not random, that any correlation that you're observing is real, and that a treatment is having a statistically significant effect. So if we get a p-value that's less than 0.05, your null hypothesis is rejected because it's suggesting that there's a 95% chance that there is a correlation. But if we get a p-value that's greater than 0.05, the null hypothesis has to be accepted. It suggests that there is no correlation. So once we have all of our other calculations, we can then push through to get our actual p-value, which you calculate using a t-statistic. So how you get it is you put equal t-distribution, and we won't go through the whole like what this means because I think that's kind of too much. So let's see, we're going to get, okay, yeah, E60, E59. Okay, so how the t-distribution works, t.distribute, is you're going to get your t-statistic, whatever that was calculated, and then you're going to, the next value is your degrees of freedom, which is however many trials minus 2. And we are doing a two-tailed distribution test because we want to catch whether or not there was an increase up or down. We're not choosing a direction here. So that's what the t-distribution two-tail is going to give you. So that will give us a p-value of 0.84. And since 0.84 in this example is greater than 0.05, in this case, my null hypothesis would be accepted, which of course was to be expected because, like I said, I just randomly generated these numbers here. So when you do this, you're going to get a different p-value. Maybe you have different numbers of n groups. So this template is just here to help you. Again, remember that your pairs have to match in location and time frame. So these are already set up to calculate your rank averages, to do your squares for you, your difference in sum of squares. All of this is already set up, but you do need these numbers to write out this equation. Again, this is required that you show your work for the statistics. Okay, so that's it for the database tutorials. Again, I'm available over email if you get stuck or you need help or anything like that. All right.